180-degree mode of operation of three-phase inverter. The inverter can be operated in 180-degree mode or 120-degree mode of operation by giving the switching signal at 180 degree and 120 degree respectively. Figure A shows three-phase inverter using 6 thyristors and figure B shows three-phase inverter using IGBTs. Now this three-phase inverter can be operated in 180-degree mode and 120-degree mode by giving the switching signals to thyristors and IGBTs. In this lecture, we'll be concentrating on 180-degree mode of operation. The figure shows the waveform for 180-degree mode of operation of voltage source inverter. In three-phase inverter shown in figure A and B, each SCR conducts for 180-degree off cycle. The thyristor pair in each arm, that is T1, T4, T3, T6 and T5, T2, are turned on with time interval of 180-degree. It means that T1 conducts for 180-degree and T4 conducts for next 180-degree cycle. Thyristor in upper group or upper arm, that is T1, T3 and T5, conducts at an interval of 120-degree. It implies that T1 is fired at omega t is equal to 0 degree, then T3 must be fired at omega t is equal to 120 degree and T5 at omega t is equal to 240 degree. Same thing is applicable for lower groups of SCRs. That is, the upper group thyristor T1 from upper group conducts for 180-degree, thyristor T4 for the next 180-degree, and then again thyristor T1 for 180-degree, so on. Whereas thyristor T3 from upper group starts conducting for 180-degree after T1 starts conducting. After T3 conduction for 180-degree, thyristor T6 conducts for next 180-degree and again thyristor T3 for next 180-degree and so on. Whereas thyristor T5 from the upper group starts conducting for 120-degree after T3 for 240-degree after T1. After T5 conduction for 180-degree, T2 conducts for next 180-degree, T5 for next 180-degree and so on. In this manner, the pattern of firing the 6 SCRs is identified. Now, this can be studied in using the equivalent circuits. These equivalent circuits are modeled in 4 steps. So step 1 and step 2 are shown in the figure respectively, that is for 0 to 60-degree, step 1, step 2, 60 to 120-degree, third step 120 to 180-degree, and fourth step 180 to 240-degree. So all this circuit shows equivalent circuits for conducting the upper and lower group of thyristors in a manner of 180-degree mode of operation. Using this equivalent circuit, we can find out the current and line to neutral voltages in the particular circuit. We will be concentrating on two steps in order to find out the current and line to neutral voltages. So during step, that is when omega t is greater than 0 and less than pi by 3, thyristors 5, 6 and 1 are conducting. At that time, the current flowing through the circuit as per the equivalent circuit is I1 is equal to Vs divided by Z plus Z divided by 2 is equal to 2 by 3 Vs divided by Z. And line to neutral voltages are Va0 is equal to Vc0 is equal to I1 into Z by 2 is equal to Vs divided by 3, and V0b is equal to I1 into Z is equal to 2 Vs divided by 3. Similarly, for step second, that is when omega t is greater than or equal to pi by 3 and less than 2 pi by 3, thyristors 6, 1 and 2 are conducting. At that time, for the equivalent circuit shown in step 2, the current flowing through that circuit is I2 is equal to 2 divided by 3 into Vs divided by Z, and Va0 is equal to I2 into Z is equal to 2 Vs divided by 3, and V0b is equal to V0c is equal to I2 into Z divided by 2 is equal to Vs divided by 3, or Va0 is equal to 2 Vs divided by 3 and Vb0 is equal to Vc0 is equal to minus Vs divided by 3. So these output voltages are plotted in the waveform. In this manner, the variation of phase voltages, that is Va0, Vb0 and Vc0, are obtained from the equivalent circuit up to step 4, and similarly for other step is plotted in the waveform. It is clear that for each cycle of output voltage of each phases, 6 steps are required and each step has duration of 60 degree. The line voltages, that is VAB is equal to VA0 plus V0B, or VAB is equal to VA0 minus VB0, is obtained by reversing the neutral voltage with respect to B phase, that is VB0, and adding it. Similarly, the line voltage VBC is equal to VB0 minus VC0, and line voltage VCA is equal to VC0 minus VA0 are plotted in the waveform. Now, using the circuit, we can find out the 3-line output voltages using the Fourier series, as VAB is equal to summation n is equal to 1, 3, 5, 9 up to infinity 4 Vs divided by n pi cos n pi by 6 sin n omega t plus pi by 6. Similarly, the line voltages VBC is equal to summation n is equal to 135 up to infinity divided is equal to, in summation it is 4 Vs divided by n pi cos n pi by 6 sin n omega t minus pi by 2. And similarly for phase C, or line voltage with respect to C, is VCA is equal to summation n is equal to 135 up to infinity 4 Vs divided by n pi cos n pi by 6 sin n omega t plus pi by 6. For n is equal to 3, cos 3 pi by 6 is equal to 0. Thus, all triplet harmonics are absent from the line voltages and are given by the equation as discussed above, that is VAB, VBC and VCA. Similarly, the Fourier expansion of the neutral voltage, that is VA0, is given by equation VA0 is equal to summation n is equal to 6k plus minus 1 to infinity 2 Vs divided by n pi sin n omega t, where k is equal to 0, 1, 2, 3, so on. So for linear star connected balanced load, phase or line current can be obtained from the Fourier expansion, that is VA0. Similarly, the expression for VB0 and VC0 can be obtained by replacing omega t by minus 120 degree and minus 240 degree respectively. The RMS value of nth component of line voltage, that is VLN, is equal to 4 Vs divided by under root 2 into n pi cos n pi by 6. The RMS value of line voltage, that is VL1, is equal to 4 Vs divided by under root 2 pi cos pi by 6 is equal to 0.7797 Vs. So from the waveform for VAB, the line voltage is Vs from 0 to 120 degree. Therefore, RMS value of line voltage VL is equal to 1 divided by pi integration 0 to 2 pi by 3 Vs square d omega t raised to 1 half is equal to under root 2 by 3 into Vs is equal to 0.8165 Vs. Similarly, the RMS value of fundamental phase voltage can be Vp is equal to VL divided by root 3 is equal to root 2 by 3 Vs is equal to 0.4714 Vs, and phase voltage Vp1 is equal to 2 Vs divided by under root 2 into pi is equal to 0.4502 Vs is equal to VL divided by root 3. So in 120 degree mode of operation, we can say that the thyristor, each thyristor conducts for 180 degree of operation. That is, if I consider one arm T1, in one arm we have thyristor T1 and T4. That means thyristor T1 will conduct for 180 degree mode of operation, and in next cycle thyristor T4 will be conducting for 180 degree mode of operation in next cycle. So the upper group of thyristors, that is T1, T3, T5, conducts for interval 120 degree, and similarly it is applicable for lower group of thyristors. So this is about 180 degree mode of operation of three phase inverters.